I start. So last time after talking to the TA, we decided to extend the deadline for 1 week. Right? So to accommodate your um, the availability of GPU, right? But this will be the final extension, right? Don't expect we have further extension there, and it's a special situation, right? So um, yeah, try your best to finish it on time, and even if you are late, right? Submit, and we will try to see how much we can do for the even for late submission. Okay, today let's continue. Share my script. Okay, last time we okay, it's here. Okay, I checked the Google file system original paper. So let me pull it out for you. Because the last figure is looks very weird. And let me copy this part. Okay. Okay, so I put it here in the, maybe I can put it here so that you can see that more clearly. Um, right, basically it's a performance. So here it's the setting is important. So n clients append simultaneously to a single file. Right. Therefore, the performance bounded is limited by the network bandwidth of the chunk servers or the last chunk of the file. Right, because you are trying to append there. Right. Right, when you write to a file, the file has multiple chunks, right? So you can write in parallel. But your append is basically the last one. Even though n client try to write at the same time, actually you can see the aggregated rate may even decrease because of the configuration they have. Right. That is a message from last time. Right. So the remaining one. Okay. So they did an evaluation on two clusters, right? As we discussed, that is a very common. One is for RDD. It's a small cluster, and the task normally run up to hours, right? So people try something there. And the cluster B is for production use. It's a continuous phase customer, and it generate a lot of data, and the tasks there are long running. Right? So basically, we can see the performance here, right? So A and B have both 300, 200 servers, and you can see the disk space, right? For the production one, it's even larger, even though the number of chunk servers is smaller, right? Basically means on each chunk server, they have more disks, right? And utilization, right? You can say more or less the same, right? And files, dead files, right? You can see a lot of dead files. I mean, especially on the production server, right? A lot of dead files, right? It's a result from the lazy garbage collection. And the number of chunks, right? In both cases, right? Roughly is 1 to 2 chunks per file. And the metadata at the chunk server is very large, right? But at the master node, it's much, much smaller, right? Due to the reason we discussed last time. Read and write rate. Right? So take a look, right? First, right, before I explain that, try to figure out what happened here. Here you may notice some trend as well, and can pull out the original paper for the explanation. Basically, setup both cluster has been up for about 1 week, and the clusters also had been restarted recently to upgrade to a new version of the Google file system. And so I guess you may notice some trend and something that is a little bit strange, right? So the general trend is that you see the write rate is much higher than the write rate in both cases. Right? And for the production server, the write rate is actually much better than the cluster A, the R&D one. Right? And also the master operations, right, is not very high. Right? So each second only process hundreds of operations. Right? So it's not a very big pressure on the master node. Of course, you may notice something weird, right? Because here the read rate is very low and the write rate, right? So basically, uh, it mentions that when they took the measurement, B was in the middle of a burst of write activity, generating about 100 megabytes per second, which produces a 300 megabyte network load, right? And because they need to duplicate it 3 times. Uh, right. Also, both classes were in the middle of a heavy read activity. Right. So as you can see, since restart, our average is not that high for B, right? But the current burst will be several times higher than the average one. Right. Okay, that's a message here. Recovery time. Right. They basically kill one chunk server, right, to mimic the behavior of a failure. This chunk server, it contains like a 600 gigabyte data and 50,000 chunks. So all the chunks are restored in 23 minutes, right? So that is the speed. If you kill 2 chunk servers, right? So because each chunk you may have 3 replicas, right? If you kill 2 chunk servers, it's possible there will be some overlap. Therefore, some chunk only have a single replica. In that case, right, so they will prioritize the single replicas, right, to restore them to at least 2 times within 2 minutes. Right. Of course, the remaining you can imagine it's still restored roughly in 20, 30 minutes. Right. Here you can see also the reason, right, why you don't want to put the chunk on the same server or even the servers within the same rack or that are nearby to each other. So clearly, right? So in Google file system, right? So users they put they support a lot of users, a lot of workload on the same set of servers, right? So they may interfere with each other. Therefore, right? So how to limit that one is clearly a challenge. And they also notice some of the biggest problem with disk and Linux related, right? And mm, as I mentioned before, right, disk, they contain more mechanical component there, right? So it's more likely to have the issues. And the Linux, right, because it's open source, they have more problem. But likely, right, with because it's open source, they can also easily explore and understand what happened there and to fix the problem. Right? So over time, I think now Linux system is also much more stable than before. And the disk, because we start to use more and more SSD nowadays, right? I think that also become more reliable. Okay, comments. It's tailored for Google's workload, right? We discussed this. And it interact with MapReduce, which is a major application for Google at that time, right? So there is a performance volatility, right? That change over time. Okay, now we move to MapReduce, but before that, any questions? Okay, by the way, before we moved on to the MapReduce announcement, uh, so next Tuesday is our fall break, so we don't have lectures. And next, the Tuesday after next, October 22nd, we will do our midterm check. Um, so you guys already did the proposal. Okay. So this one, the proposal is done on September the 24th. Right? Basically, when we do the midterm check, it's already 4 weeks from the proposal, right? So we want to check what happened. And the guys are, let me check how many groups we have. I think we have a lot of groups. Yeah, we have 28 groups. And in that case, so 2 minutes per group and one group member. Basically, you ask the group leader to present and send me your slides beforehand, before the lecture, and the subject line with a group number so that it's easy for you to search to get it. So yeah, what to expect? Yeah, I'm just doing that. So basically, in that case, you basically have two, yeah, you can still have 3 sides. So first side is just a review of deliverables proposed. And the second side is what you have done on those deliverables. And the third side is timeline for the rest of the semester on finishing those deliverables and any and also the challenges. Okay. So the goal is that to check that yes, there is a suggestion to have everyone recorded and uh, yeah, I mean Mm, yeah, let me think about that. So far, for all the uh, for all the previous offering of this class, um, the proposal, the midterm update, and the final presentation, they are all done in person instead of doing the recording. Um, Partially, the reason is that I would like you guys to present I mean, in person instead of recorded, right? So, I mean, this recorded one, it's basically when we have no other options, uh, which people during the pandemic, people were thinking that that might be the future, but clearly it's not the case, at least for now. Right? You see major companies now basically ask people to go back. And uh, so basically most of them, many of the meetings of the presentation will be done in person. And even before remotely, it just remotely. It's not something you can record and do that. So from the learning of the training perspective, so it's very different. Uh, I can see the student when they record and when they present in person, it's also very different. Right? So I think unless there are something, for example, the I was hoping that you can do your uh, group presentation as well in person or remote, but it seems that we don't have enough time, so we remove that component. But for this one, I think we still want to do that. The other reason is that in an interactive way, I can quickly get what you want to do and uh, ask you question, give you some feedback, which is not very easy to do in an asynchronous way, right? Because in that case, even you submit your recording, by watching it, I cannot ask you a question. So in that case, I need to ask you to come to my office and then basically I watch the video and then ask you a question and then it's even it's not very good, right, to do it in a distributed way. Okay, so I think I think I will still do this one, and we just because we have more groups, we will make it shorter. But I still think it's better than uh, you just submit a recording and then I mean with the recording it's really hard to give feedback and to for some group if you are doing not very yeah it's hard yeah and also in that case you cannot say how each other works right so I think uh, the awareness of how other groups are going I think is also important. I suppose if I just ask you guys to submit your recording and then even I release it to everyone, I doubt how many of you will watch the presentation or recording from others. Similar to the student presentation, right? If I just release it, the recording will be connected. Now you can ask yourself, right? Will you go over each of the presentation, right? Or you just will basically ignore them. So again, I think the situation now is that knowledge-based stuff is becoming less valuable because, as you can see, larger models are doing very well. Right? On the other side, right? So if you want to gain other capability skills like a presentation, like a project, right? Uh, like the only way is that you need to do it by yourself and do it in the real world. Right? So that's right. So that's why I think those components are still very important and valuable. It's just sometimes we face time constraint, we cannot go for it. Right? But whenever we can, I think we should do that. This basically, I think the challenges I can tell you for the midterm check is that 2 minutes is very fast. Right? But actually, for some group, even you give them 5 minutes, they may still completely off the topic, right? So they are not directly to the point. That's why we give you this particular format, right? So basically, you don't need to go for anything other, right? Just tell us what are the deliverables you propose. What is the current status on each of the deliverables? And what is your plan? You try to finish them for the rest of the semester. And what are the challenges you face? In that case, we can see clearly what happened in each group. And you can see also from the peer groups. And actually, to be able to present in a very short time period is also, I mean, skill you need to do, because in the future you will have a lot of situation that you are only given limited time, but you want to make something very clear and also uh, try to get some opportunity. Okay, so any question about the midterm check on the Tuesday after next? Okay, great. So I very much look forward. And also preparing this will also give you a heads up. Right? You may have the feeling that whether you are ahead of your original schedule or if you already fell behind. Right? In the later case, you probably want to figure out what happened and how to recover right from it. Okay. So, uh, okay. Every news. So the motivation, I think I discussed that in class before. Right? So there are a lot of special purpose parallel computation, but right, there are a lot of things we need to handle the details, right? Uh, and which is time consuming, but it's common across the different parallel computing, so that we can develop a system to simplify those, right? So user don't need to worry about those details. Okay, the design decision. First, they only do map and reduce. Right? At that time, it was very uh, helpful. Right? But of course, later, as you know, from Spark, it go from map reduce to the general DAG. And now for GPU training, right, or inference is also very different, right? But it's just that at that time, particular for that maybe 10 years, right? So it's very useful, right? And very relevant. But as time goes, right, clearly you can see it will go down. And here, fault tolerance and scalability, right, should come without user effort. Scalability in particular is still very important nowadays, right? And I think try to minimize user effort is still important, right? Fault tolerance similarly, right? Now GPU cluster also need both of them. Deterministic work, right? This is a little bit different, right? So traditionally, rerunning the MapReduce, like what I mentioned to you, the word count or other examples, right? To process a document to do the indexing, right? To calculate the word frequency, something like this. It's a deterministic work, means that you rerun the workload, you will get the same output, right? So now it's a little bit different. Can anyone think about why? What's the difference nowadays? For example, right? In now machine learning, AI machine learning training, is that deterministic or is randomized? If you know the answer, you can put it in the meeting chat. Right. So I suppose you guys have some background in machine learning, right? It's randomized, right? So from the at the beginning, uh, the initial weight, right, and also the training process, right? Whether you have the dropout or many sense, they're randomized, right? Therefore, you rerun the same training, you may get a slightly different output. So, but for MapReduce, their job is much simpler. So it's a deterministic work. And the level of parallels, this is primarily decided by the file system. Right? So basically, if you do the work count, if you have for the files, if you have 1,000 chunks, basically you can create a 1,000 map. Right? Each map work on one. If you have only 10 chunks, then you can have 10. If you have a 1 million, you can do 1 million. Right? So you have a little bit control over the reduce task, right? As we discussed before, each reduce just process a certain range of the intermediate result, right? Therefore, you can decide whether you want to 1 reducer, 10 reducer, or 100 reducer, right? Then you can control it. But the map part is harder to control. Right? So this is regarding level of parallels. Okay, so question for you guys. So do you know that for uh, now the large model or the large model training, right? AI machine learning training, what is the parallels level of parallels decided? If you know something regarding the parallels in AI machine learning, those neural network training, right? Put it in the meeting chat. Right? Let me see how much you already know. Right? So distributed over available GPU memory in parallel, right? GPUs, right? You know. So let me ask you one step further, right? So in terms of the parallelism, so do you know the different type of parallelism? Okay. One type is called data parallelism. Do you know the other? Major, right? Of course, there are multiple small names, but one is data parallel, meaning that I say I have a 1 billion training samples, right? I can spread over 1,000 GPU, and each GPU only process 1 million of them, right? So that is a data parallel. Each node still run exactly the same model. So on each GPU, it's just the same model, but the data is different, right? So the this is they normally use a parameter server architecture, right? So there is server that hold the parameter, right? So each GPU they train using the local sample, local data, and then they aggregate and then send that back for each epoch, right? So that's one way called data parallels. Do you know the other one? Yeah, the other one is model parallels, right? So the data parallels is much easier to implement. That was uh, the dominant that parallels before 2020. After 2020, so we have the model parallel. That's because the model size is larger and larger, right? So there was a paper called the scaling law. Right? It basically shows that the model architecture actually doesn't matter much. As long as you have enough data, enough computing resources, and a large model, the performance can keep increasing. Uh, After that, people start to use larger and larger models. And nowadays, right, if you go to like a Llama 3, the large model, clearly it cannot fit into one GPU. We discussed before, right? The GPU have a limited memory, even though it's not small actually. The GPU may have a 40 gigabyte of memory, right? It's probably better than your laptop, right? And it's only a GPU card. But the 40 gigabyte memory compared to the current model size, right, is very small, right? So one GPU cannot hold the whole model. Therefore, we need to divide the model into pieces and put one piece on a GPU. But the downside of doing that is that then even for just one epoch, the GPU need to communicate, right? Because it's basically just pieces of the same model across the GPU, right? So of course there are other model parallel, like people also mention pipeline or something, right? But at the high level, right, there are data parallel and the model parallel are the major ones, right? Which clearly you can say is very different from the MapReduce work, right? So the message is that each particular system is designed for the particular application. You need to make the design decision. You basically you cannot develop a one system fit all. Okay, so I have this figure basically remind you, right? So to hide all the details, it matters a lot, right? Because in the old days, they have this BlackBerry, right? Have all the keyboard here, right? You can basically have all the control, right? Later, you go to the iPhone. Right? iPhone at the beginning they only have one button, and now they basically remove the button on the screen, right? So everything else is hidden, right, behind So as a user, your experience is much better, right? This is something similar to what MapReduce or Google File System or even nowadays Kubernetes, TensorFlow, or all those systems trying to do is to hide the details for the user so you can focus on what you want to do. Right. Programming model, this is a simple, right? Let's use a simple example, workout. Right. So let's say you have three documents, right? Each document have some words. And this is the data, right? Let's say this each document you have one chunk. Right? So we want to get is that we first process each document, right? So you have a result like document one, we have apple appear once, banana appear once. Document two, we have banana appear once, orange appear once, and document three similarly. And this one, clearly we can process it in parallel, right? And the code you write, you run on each of the mapper, right? On each of the server is basically the same. And then after we have that one, next step is that we need to aggregate the result, right? Eventually we say for each word, actually it appears twice, right? So how that work, right? You do the local calculation, and then you do the shuffle, right? Had the intermediate result, and combine them, aggregate based on the key. Right? Here, the key is the word, and the value is the occurrence in that document, right? So then you aggregate based on the key. So basically for Apple, it appear once, and once combine them together, you eventually get the result, right? At a high level one. And so this is a three stages, right? You petition to the map, and then you do the shuffle, right? And then finally you collect the result, right? So the remapping, the first time for the map, originally for the document, it's a document ID to the content. And from there, you convert it to the new keyword key value pair that is from the word is a key and the frequency is a value. Right? Reduction is just you aggregate them, right? From the duplicate keys to distinct keys, right? You combine the same ones. And of course, there will be the question, right? How many partitions for the map and reduce? As we discussed, normally the map is based on the document. But if you have a lot of small document, right? Let's say you have a uh, right, so 1 million those kind of tasks, right? 1 million files, right? So you probably don't want to create you don't have access to 1 million servers, right? So even though you maybe have 1 million chunks, right? 1 million mappers, then you need to run one by one, right? But then if you only have 1,000 servers, that means each server need to process 1,000 maps, right? So that's a little bit weird. So another way is that you can aggregate even from the map stage. Or reduce, right? Clearly you can do a lot of things. Scheduling, right? Once you have map, right, how to assign workers, right? And how coordinate between map and the reduce workers, right? And finally, for fault tolerance, what if something fails? So the real world basically is first you get the map worker and the reduce worker, and you split the document, right, to some extent, right, to go to AMS place. So each split may contain a certain number of documents, depending how you choose M. Right? And with this M chosen, right, across the split, it also try to do the load balancing. Right? The most easiest way is just based on the total size of the doc. Right? The underlying assumption could be right, the workload is proportional to the size of the data. Right? So you have the split, and then for reducer, you can choose to have R reducers, right? Then it will also aggregate to the R different range of the word as a case. So that means in the intermediate result, you will have M times R partitions, right? So each split, once you get your intermediate result, that need to be sorted first, and then split over the R regions for and selected decided by the reducer. Therefore, in the intermediate one, you may have M times R partitions. Those are actually basically stored in the disk, and the disk, the mapper there is a shuffle stage that is trying to send the data to the reducer. Or you can think about the reducer basically read the data from the intermediate result written on the disk. Right. So underlying, right, you can imagine it's a Google file system. Right. It has the data for each mapper, for each map worker. Right. So in that case, right, so clearly if you have the data local, it's better. But if you don't, you need to read the data there. And the output, finally, it's again write back to Google File System. So you need to, as a user, you only need to write the map and the reduce functions. Of course, if you want, you can do the configuration of how many mappers, how many reducer, right? Other hyperparameters you want to choose. And the master node of MapReduce will manage all of those, right? So manage the map worker and reduce worker, and also to coordinate the shuffle stage. Therefore, there will be on the order of M plus R task status because I combine both M map tasks and R reduce tasks. And the state is based on the location, right? Basically the shuffle stage. Right. So when we do the map worker placement, right? Select which server you want to put the map work on. So we basically try to utilize the locality, right? Right, okay. So of course there are some refinement. Right? First one is called stragglers. Right? That is I think I discussed before, right? If you run 1,000 map tasks, right? But when a large number of them have finished, right? Let's say 95% already finished. There are only 50 map tasks left. But in order to do the reduce, right, we need to wait for all of them to finish, right? So these 50 remaining tasks may be considered as stragglers, basically drag the system down. And what they do is that for those 50 ones, we will duplicate those tasks on other servers. Right? So hopefully some of them may be finished faster. This is the called uh, speculative execution. Right? We just try to do that speculatively. Right? I hope some of them may finish faster. Okay, so in that sense, let me ask you two questions. The first one is that in order to start a reduced task, do you need all the map tasks to finish? Yes or no? You can put it in the meeting chat. Okay, so here is a little bit complicated, right? So by default, it's a yes. So you can see here, in our example, right? To count the occurrence of a banana, right, in all the documents, right? You actually need for all the map tasks to finish, right? Otherwise, you don't know the correct answer, right? So basically, we should let me put in the meeting chat to highlight it. If we want to have the correct answer, reduce worker has to workers have to wait until all map workers finish their right. But when you say no, it also makes sense because in practice, especially for MapReduce, Google use, they basically can skip some result. Let's say out of 1,000, right, 50 are very slow, so they duplicate them. And after that, still two or three of them doesn't come back, right? So they basically will ignore that and then finish the work, right? But you should know that by doing that, your result is no longer 100% correct, right? In the situation where we require the correct answer, right? You cannot ignore any map task. Then you need to finish all of them, right? Which is normally the assumption for many tasks now. Right? I think for training nowadays, it's also by default you cannot skip any of the training samples. Right? You basically do that. Okay, similar question, right? So the middle stage is a shuffle. Can shuffle start before all my worker finish? assuming we require correct count. We need to get the correct answer. The reducer cannot start until we all the mapper finish. But how about shuffle? Yes or no? Shuffle is basically to read the intermediate data, right, from the uh, map stage to the reducer, right? So basically, it's a middle part. Yes or no? Yes, right. It can start, right? Actually, they can start as early as they only finish maybe 5% of the map task. So because for mapper, the first mapper working on split one, it doesn't need to wait until other to finish, right? Once no matter whenever it finish its own task, it can start to send the data to the corresponding reducers. Right? Actually, by doing this, we spread the traffic, the networking traffic, right, across time. Right? So it's actually good for the load balancing in terms of in the time dimension. Right? Okay, which we can also see from the evaluation part. Right? Okay. Uh, so there are some others, right? Like uh, so yeah, those are just details. Okay, performance. So you can see for here the time, right? The input, right? When we read the input, it can go up significantly, and of course, when they finish, it goes down, right? So for 1800 machines, right? They basically can read 1 TB of data in parallel, right? Right, and it's also the peak rate is 31 gigabyte per second, right? But this is greatly uh, due to the locality, meaning that you just read from the local disk. As otherwise, if you need read from the rack switch, right? The rack switch capacity is at 10 gigabyte per second, right? But you can see here, 30 gigabyte per second, at least 21 gigabyte per second was actually found by reading the data locally instead of going through the rack switch. And also, you say there is a significant startup cost, right, which is here. That is, if you are familiar with TCP, that is actually due to the TCP congestion control, right? So, and you read also you when you read the local one, even the local disk is also have the issue, right? So let's give people the motivation, right? So if we already know that you need to do a lot of things, right, later, then probably we want to reduce this stage, right? Because in the data center network, you know a lot of more information compared to the wide area network, right? You don't need to do it so conservatively, right? You can do more aggressively to reduce this stage, right? Because otherwise, you say in this case, the job finish around 80 seconds, right? But the start stage take half of the time. It takes more than half of the job duration to reach the peak, right? So that is clearly a significant slowdown. And let me show this figure and let me switch the order a little bit. Yeah, this is another result figure. So normal operation, you can say the input is basically for the map task to finish, to process. You can say it process the data here. Probably around 250, right? It finish all the map tasks, right? Basically, at this time, the map start. And the map actually take a long time to finish. But the shuffle start very early, right? So and it take also a long time. That is probably the reason why reduce also take a long time because a network is a bottleneck here, right? It first send a lot of traffic out the shuffle, and then send here it's another shuffle. You can see here significant traffic here and reduce. Right? Basically, that answered verify the question we just asked. Right? Basically, in normal case, the reduce should start after all the map finish, but the shuffle overlap with the map stage. Okay, and then you basically they queue some of the tasks. Oh, sorry, this is a no backup task. If no speculative execution, right? Uh, in that case, right, it takes much longer. At the beginning, 800 seconds, right, it's similar, but only a small number of tasks will keep running until 1200 seconds. Right? So basically, if you don't duplicate them, a small number of tasks remaining there can drag the whole system, right? Make the duration 150% longer. Right? That is a benefit by duplicate some tasks at near the end. Okay. Here it shows that if we kill 200 processes, right? So you can say the map task, you kill some of them, it's still trying to recover later. And the shuffle, right? Basically, in this case, right, the computing time is more or less the same, right? Basically show that the system is robust to killing some tasks, killing some process. Okay, this figure, right? Let's go over this one. Right, the techniques used, right? So replication, right, is used in Google file system, right? They duplicate the data. Erasing coding that is also used in Google file system, right? File system. And the partitioning is used in both MapReduce and GFS. Load balancing, right? This is automatic due to the partitioning, right? It's also used in both of them. Health check, integrity check, used in both cases. Preparation is actually also used in Google file system. Eventual consistency is used for Google file system master node. Centralized controller is for both of them. Canaries, right? We didn't. It's not applicable here, right? Because it's already a full developed system. Redundant execution, right? That is used in MapReduce. Okay, to summarize, we see question here. Yeah, I think the question is about it's here, right? So they have some negative traffic, right? Oh, yeah, I'm not sure. I mean, that's a good question. Then let's check the MapReduce paper. Yeah, let me share this one with you. Yeah, this is a good catch. I didn't realize this one, but let's see. You can see this figure, right? So let me see the figure 3C. Okay. In figure 3C, we show the execution of the sort queue worker several minutes into the computation. It's basically something at the beginning. And then cluster restart as a, oh, it's basically, it's not the negative one. It's just they basically represent the worker death as the negative input rate. Since you probably previously calculate something, but then when the server fail, right? Also when the map fail, let's say you first consider I finish 5%, 50% on a particular map, but when it's fail, it go back to zero, right? So that shows the in the negative one. Yeah. Okay, good. Yeah, that's a great question. Thanks for pointing out. Okay, to summary, right? So first one, use domain knowledge wisely. It works for GFS and MapReduce. It also works nowadays. Right? As I mentioned to you, right, for both computer science and data science students, the job market is becoming more challenging for you, right? Because I heard some rumor, right? So for coding part, right, now ChatGPT or other models can do coding fairly well, the Copilot, right? And previously, if you just do some lead code, and try to get now those AI models can do the coding much more effectively than if you just learn by yourself. And debugging, right? I heard also AI can do very well, right? Those some large companies, right? Internally, they can rely on the AI to do most of the debugging for themselves for their systems. Right? Similar for tests, they can do the same, right? Data science. Right? So now if you search, you may get some codeless data science. Right? Means that traditionally you need to write the Python or R code to process the data. And now you can just use a large language model. Without do any program, you can just use the natural language, right? To ask the AI to do the data science task for you. Right. So what does that mean? That means, right, a lot of the tasks are already replaced and will be replaced more, right, by AI. Right. What's left? Right, it's basically the AI combined with the domain knowledge. Right. Like nowadays, you say both Nobel Prize for physics and for chemistry both go to AI, right? Highlighting the importance, right, for AI to work combined with the domain knowledge and to right. The AlphaFold is just a starting point, right? We hope clearly more systems like this, right, to further improve the scientific discovery, uh, because our pace is too slow, right? With AI, we can hopefully do much better, but it's definitely non-trivial, right? So how to combine data science, computer science, AI, right, with domain knowledge that is non-trivial and valuable still now. Second is that strive for simplicity, right? It's still the case, right? For current AI training systems like Kubernetes, like CUDA, like TensorFlow, PyTorch, all of them, right? They still try to achieve this, hide all the details, right? So that you can just focus on doing the training, right? Even now with the scaling law, even the training itself become more simple, much simplified. Previously, you need to worry about the model architecture details, right? Now, basically says that you don't need to worry about it. You can focus on getting more data, right? Making the model large, right? So getting more computing resources, right? So it's basically make everything much simpler. Right? And fault tolerance and scalability, right? They are still required, right? Nowadays, probably more important today in AI machine learning, right? The distributed learning part. Okay, so sorry, I need to share this. Right. So this is a summary, and I probably didn't share this part. Right. This is a techniques used. Okay. Any question about this one? Or we now we finally we can go to the web structure. Okay, let me share this one. Okay, so web structure. So what we want to say, what kind of structure we can find in the web graph, right? So uh, the like many Google and social network, right? And I think maybe in the AI machine learning, right? So we will see some architect structure like this, right? So today's goal is to understand the property of the web structure, right? So here, each node is just a one web page, and the directed edge represent the links, right? Those can be navigational, right? Early days, right? Now even do some transaction nowadays, right? So basically the link will point content in one page, web page point to another web page, right? So as a HTTP link there, right? So first of all, the web structure is man-made, and it's not something like happen natural in the world. Right? But at the same time, we don't have explicit control over the web structure, right? So the updates are made by individuals in a distributed way, right? So this is very interesting, right? So it's go from zero, right, and basically grow into the current web structure, right, and in a distributed manner. So question, I think about what properties should we look at? Right? At least some of them there, right? We can think about, right? We can look into like a size, right? Basically, how many nodes are there? And the density, how many edges do we have? Connectivity, right? How the network web graph is connected. And also for vertex, the degree and the diameter, going from pick any two nodes, how many steps we need in the worst case, right? Between them. And the clustering give us communities, right? So we can go through some of them. Right? First, for connectivity, right? So the definition. So the DAG, I mentioned sometime, right? Because like Spark or other system, they require the job, the tasks follow a DAG, right? So DAG is the full name is a directed acyclic graph, right? So let's say a graph G is a DAG, means that you pick any node U and V, right? So you cannot find a circle there. Meaning that if there is a path from U to V, you cannot find a path from V to U. Right? Otherwise, you create a cycle. Right? For example, the graph I show here, this is a DAG. Right? And if you from there, we see the graph if it's a strongly connected. Right? Basically, here, if you pick any two uh, node U and V, you will find the path in both directions. That means the graph is highly connected or strongly connected. Right. From the previous graph, if we add some additional edges, we can make it strongly connected. You can check, right? You pick any two nodes. For example, if you call this is U, this is V, clearly you can find the path come here, and you can also find the path going back, right? And from there, we can also say, because the weak, strongly connected part, right, means that those nodes have are very close to each other, right? It's kind of a community. Then we can from there get the strongly connected component or ICCC. So this is set of a node, right? Within the node, it's a strongly connected, right? And you cannot find a larger one, right, to contain this one. So this is the maximum, right, that you can find, right? So in this case, and a special case, right, if you cannot find this one, so each node is an ICC by itself. This is a definition, special definition, right? So in the special graph, this is a DAG. In the DAG, by definition, there is no cycle, right? So basically, each node is an ICC. But if you add some edges there, we can create something like two ICCs here, right? So these three nodes, they can connect to each other and in cycles, right? So these three are ICC, right? There is another ICC, right? Actually, from here, we can say if we consider this is ICC1, this is ICC2, then if we consider each ICC as a single node, so this is ICC1 and 2, the remaining edge is here, right? So it's much simpler, right? So this you can consider these two communities, 1 to 2, and there is an edge pointing from 1 to 2, right? So this will give us a question, right? So if we consider each ICC as a node, what is the remaining graph, right? The graph connecting the ICCs. So question is that what is the graph connecting the ICCs? Right? As I just showed, you can say on the left-hand side, because each node is ICC, so the ICC is the graph connected ICC is just the graph itself. On the left-hand side, right-hand side, it's just two ICCs. The graph connecting ICC is just going from ICC1 to ICC2. So what can we say about the graph connecting the ICCs? Any idea? Right. So it's a DAG. Right. So of course, here is another definition, weakly connected. Right. So basically, the graph connecting the ICCs is a DAG. Right. You can think about why this is. Right. In 2 minutes, right, we will work together this out. Right. Why the graph connecting the ICCs is a
Fester, I think you're muted.
Yes, I'm muted. Yeah, so you can think about this one, right? Anyone get an idea why this is the case? See if I have the proof here. Okay, so basically for the requirement of the DAG, right? So there is a no cycle in that one, right? So let's say if the graph connecting the ICC is not a DAG, right? Which means you should be able to find U and V, the ICC U and ICC V, and there exists a cycle, right? Basically, it's a path go from ICC this U to V and V to U. But if this is the case, then you basically can combine these two ICCs into a larger ICC, right? So this contradicts with the definition that the ICC should already be the largest one locally. Right. Okay. Also, right. So the previous one, basically a DAG has no ICC larger than one node. Right. Otherwise, it's not a DAG. Right. If it's a contain ICC larger than one node, right? Let's say it has two nodes that has a path going from each other, right? So this is a ICC, right? ICC means that there is a path from 1 to 2 and 2 to 1, right? If a DAG contains this part, then it's no longer DAG, right? It's contradict with the definition of DAG. More complicated one is that we can partition any graph into a set of DAGs, a set of ICCs. Right? Every node is in exactly one ICC. Right? So the proof is also straightforward. First, it must be in one ICC, right? Each node. And if one node is in more than one SCC, what happened, right? So if one node is in this SCC and also in SCC2, then you pick any two node that S and T here, right? Because S and U are in the same SCC, right? So there is a path going back and forth between. And U and T is also within the same SCC too, so there is a path going back and forth, right? So in this sense, you can say U can serve as a bridge for any node, any pair of node in 1 and 2. So basically, in this case, 1 and 2 should be one SCC instead of 2, right? So this contradicts the definition of SCC, right? Therefore, each node is in exactly one SCC, right? And together with the node connecting, it's a DAG. So basically, that means we can partition any graph into SCCs, and then the SCCs are just connected by a DAG. So this is a high-level message we can say for any graph. So another related definition is called weakly connected component. Right? So in this case, it's not a path from in both directions. It's a path basically in one direction, either from U to V or V to U. And again, it's the largest component. You basically cannot find a larger one to contain. Okay, I think that's all I want to. We already run out of time, so we will stop here. And any last minute question? Let me see. Post these slides on Brightspace. Yes, I will do after this. I finish. Okay, if no more questions, and have a great rest of the week and also the spring break. I will see you next Thursday.